we commence again. So, in the first part, what you learned is reconstruction of climate. Now, in this part, what you are going to learn is different techniques which are used. I am not going into details. We can discuss this maybe another time if you wanted to know the details. But I will essentially try to touch majority of the well-known techniques which are known for paleoclimatic reconstruction. So you start with something which was initially started way back in 1942 by some of the scientists working in UK, where they tried to find out the similarity between something called stomatal index and its density, the relationship of it with ambient environment. So you always define this parameter called stomatal index is something stomatal density divided by something called stomatal density plus epidermal cell density into 100, and this index is used as one of the parameters to define how the plant is responding to its environment in terms of CO2 concentration and the water use efficiency. So the advantage of using this technique is that you can go high temporal resolution, it has less uncertainty in estimation, but again, as I mentioned that if you take fossil records, I will show you some of the fossils in the evening when I am having my tutorial, that you can feel that how the fossils look like in terms of plants. You can really measure the stomatal density if you study the fossils. So you can reconstruct the fossil stomatal density and try to talk about how it has varied through time. So now this is a famous paper which came out in American Journal of Science by Roy 2001, talking about stomatal density through geological time scale. So now what does that mean? That you have to get a leaf fossils and try to measure underneath the microscope this parameter stomatal density which I defined in the previous slide. Now, people have seen in a greenhouse experiment that there is a large relationship between stomatal index, which we defined, and the CO2 concentration in species of diverse kinds. So now the relationship is rather linear, and what is possible is that you can use the relationship to talk about the CO2 concentration going back in time. Thing is, of course, you always land up in some kind of disadvantage because it is species dependent. Like one species might behave in a little bit different way compared to other species, and there can be local signals which need to be checked when you try to do such kind of experiment, trying to see that using microscope can you study the fossils and try to relate to the CO2 in the past. Okay. So now I'll straight go to isotope-based approach, and I think that many of you are familiar with this. So most of the things which you learn about this going back in time, like I talked about Milankovitch cycle, is based on ice core records. And what you do is that you study the ice, and ice has such kind of stratifications. Okay. You can see the dark and light bands. Finally, until you land up in getting something called bedrocks, where you don't see such kind of bands. So now, ice, what happens with ice gets compacted, forms like sedimentary rocks, and you can study the individual ice fraction to talk about how the climate was in terms of its temperature and in terms of PCO2 condition. We will talk each of this specifically. So what we have observed in terms of this isotope, which is oxygen isotope. So when you talk about oxygen isotopes, oxygen has two major isotopes. One is oxygen 18 and oxygen 16. Of course, we disregard this another isotope which is small in quantity, O17, because we assume that O17 is about 0.52 times that of O18. So that is the assumption which you take it, saying that there is some kind of mass relationship and there is a mass dependent fractionation which relates it. So now one can measure O18 by O16 ratio in natural materials. And how does it vary? How does this ratio vary? When you think of air, which is majority of its oxygen, is there large variability of oxygen isotope in oxygen which is present in this room and what it governs? So now this comes from a basic law of kinetics, where you see that the kinetic energy of a molecule is given by, correct? I am not discussing rather very complicated equations so that you understand it. And from the kinetic theory of gases, you know that kinetic energy can also be with the Boltzmann constant, T, temperature. the temperature present in this room will drive the velocity of the molecules. So now if you relate both of them, with half kVA square with Boltzmann constant and temperature, there is a reverse relationship. So now you can have mass 1 and mass 2 of different, when one is O18 and O16, they will fly at different speeds at one particular temperature. Will it or no? Yes. Will it? Yes. They will. So based on that, you will start thinking that yes, it is possible to model this and see that the natural system does it work well. So now one such example is when they measure the isotopic ratio in precipitation today. So now what they have observed is that there is a relationship between air temperature and oxygen isotope ratio in polar region. That is mean annual air temperature and O18 ratio in ice caps or snows which are falling as a precipitation in the polar region. So now this relationship is again about 1.4 degrees Celsius. It will lead you 1 per minute shift in case of oxygen isotope. So now you have another partner in the water, which is hydrogen. So water composition is H2O. So now hydrogen is this. You can have this deuterium. So this is also called D. So now deuterium is lighter, so it is more sensitive. It flies even faster compared to hydrogen, compared to oxygen and O18 by O16. So now you have a ratio of 0.2 per variability with temperature in deuterium. So now both this relationship people uses for predicting the temperature once you know the oxygen isotope composition of ice. So this is what the subject, what we are talking about, temperature variability, which people have tried to reconstruct if you analyze the ice samples going back in time. So the interesting things which happens about isotopic distribution is that when you have large evaporation, which mostly happen where? In the equatorial region, and finally in high latitude you go and dump them as ice, you will start getting them more depleted as you transport it to a larger distance. So there, if you see that the periphery of the ice cap, it will be rather less in terms of, it will be heavy compared to something which is lighter as you progressively go into the ice sheet. So now different regions over the ice sheet will have such variability. But of course the relative change should be able, we'll be able to see if we analyze with depth different samples. Any question?
Is there a way, are we selecting a particular site, for example, people who are doing on glaciers, so do they select a particular site depending on this, how far you are, and because that will change the composition?
Usually they,
what is the best?
Usually they maintain one particular site and do the drilling operation, and it's an extremely expensive operation, so you have to see that it should be having large communication accessibility and other communication related issue. So you use that spot and do all this measurement. Like for example, Vostok ice cap is very famous. Greenland also, there are places where they have permanent ice station where they collect these samples of precipitation and try to reconstruct that there is a large variability in terms of annual temperature. Is there a large variability of isotopic ratio? Okay, this is some kind of premise you have to do first before you start taking the ice core and try to interpret the temperature. Okay? So now, people don't rely on this temperature which is derived from my isotopic study. They say that I wanted to measure the exact temperature. Okay? Another way of measuring the exact temperature is measuring using thermometer of the kind like digital, putting it into a borehole at different depths, because you have ice going to different time. So you can measure the ice freezing temperature, which was frozen at that point of time, and try to see that is there a relative change which can be seen. Okay? So it is rather a very direct way of measuring temperature. So when you think of formation of ice, you lead to what you need to do. You have to reduce the temperature so that you precipitate the water. So now when can you have condensation? Can you have condensation at 25 degrees Celsius? Is it possible? No. Yes. I can make this less saturated with moisture. If I dump a lot of moisture here in this place, I will have precipitation at 25 degrees. So it depends on something called dew point temperature, which varies depending on the saturation, humidity. So these are all factors which plays role when you try to measure temperature. Okay? So now you can have precipitation at 25 degrees provided my air tank is saturated with moisture. Okay? It doesn't mean that I should lower the temperature then only the precipitation happens. So now when you try to measure the borehole temperature, you measure the exact temperature the ice has formed with a small change. So now you get more exact value of temperature at which the ice was forming at different point of time at that location. So this is another way of approaching this problem. So both this method together enables reconstruction to a certain extent, seeing how good they are if you talk about geological past. So now this is again another recent paper which talks about little variability of ice cores which has been taken from Greenland. As I mentioned that the previous study they have seen that is about 1.4 per mil. Now they have isolated samples which are extremely like not raining rainfall but ice, and taken very few samples to get this relationship, and they claim that this gives much better relationship compared to the other relationship where they told 1.4 degree Celsius, no 1 degree Celsius lead to 1.4 degree Celsius lead to 1 per mil variability. Here they say 1.5 instead of 1.4. And they verified it with temperature which they have obtained from the borehole and say that it is consistent with each other to a certain extent so that they can match and try to get the reconstruction done if you take ice core back in time. So now such ice core records are available from stations like Greenland, where it is easy to do such kind of drilling exercise compared to Antarctic, where the accessibility is a big problem. Okay, so now one has reconstructed back in time, as you were saying, going to about 140,000 years, where the things which I talked about, melancholy cycles, you can essentially try to figure it out. And these are called stages, where there was periods of glaciation, where there was large interglacial period and then glacial period. And somebody was asking me just during the time of tea that why it takes long time for what?
For the CO2 to
not CO2, even the temperature. So what you are seeing is that there is rapid
heating.
No, what you are seeing is temperature is going down rather slowly. It is taking very rapid change when there is dropping very fast. Okay, so now this has to do with water vapor which is present in the environment. Okay, so now once what you have is that as you start cooling the environment, you reduce the quantity of moisture which is available there in the environment, and as a result, the greenhouse effect reduces. So now what you do is that the possibility of vapor coming into picture is rather reducing. So now this one is rather very fast compared to taking this. It takes long time. Okay, to warm it. Okay. So now people have used not only isotopes, they have also measured other elements concentration. So another isotope, as I mentioned, is deuterium, but they have also measured grain size, for example, grain radius, and tried to see that is there a relationship between what has been observed in terms of isotopic record. Okay, grain size, dust, and they try to measure some kind of combination of this in terms of electrical conductivity of the materials which are present in the ice with depth, and try to compare it with the record which has been obtained in terms of isotopic composition variability. And the whole idea is that we figured it out that there was any large dust supply during the period when we experienced large glaciation. Okay? See, two common isotopes which we are going to discuss in terms of thermometry. Of course, we started. One is O16, another is O17. But the abundances of this in the nature in all materials, they are roughly about this concentration, about 99.76 and 0.2, and rest is O17, which we are not discussing because it's very small. Okay, for the time being, we consider some kind of relationship between O18 and O17 to infer talking about O17's environment. So if you think of composition of this in any kind of material, they are roughly similar in terms of percentage. But when you think of small variability, there is a large variability in terms of ppm levels. So when you think of ppm levels, you are going not in terms of percent, but you are going parts per thousand. In terms of parts per thousand, they do vary. And that variability is mainly because of processes, which are physical processes, which I mentioned here, for example, temperature. Okay, it plays a critical role in varying not to the percent level, but to the thousands level. That means third decimal place. So one such thermometry is, for example, if you think of CO2, if you combine it, you produce what? Bicarbonate. Okay, that is the common species which you find in nature. And if you put in this condition calcium, you will start precipitating something called calcium carbonate. And the person who is working on speleothem must be knowing that this calcium carbonate precipitation involves possibility of getting CO2 and water finally giving rise to this calcium carbonate. Okay, so now which one? So now if you're talking about CO2, the oxygen, two oxygen come from carbon dioxide, one oxygen comes from water, and it goes and stays there and form calcium carbonate. Okay, radical. So what happens in this process? This species, OIT, is preferentially removed from water during calcite formation. So because OIT is heavier, it has the tendency to start having preference formation of calcium carbonate. Okay, what it does some kind of partitioning, what you know as a partition function. And this effect of partitioning is sensitive to temperature. So if that is true, then the ratio of OIT by O16 in any kind of materials like shell or speleothems is temperature dependent. And this is the work which was done way back in 1950s another time by a person called Urey. Okay. And what he has done is that he can measure this compositional variability, knowing that theoretical basis that they are temperature dependent, we can expect to be, and use a mass spectrometer to do such kind of measurement and try to come up with the equation. So now this is Urey. Of course, he got Nobel Prize. Many of you may be familiar with that. He got Nobel Prize because of discovery of, have you heard of him? Any of you? Urey mineral experiment, no. He didn't get Nobel. He did it. There's the same Urey. But he didn't get it for that. He got it for the discovery of heavy water. Okay. Which was that is used as a coolant, or it retards the movement of neutrons and other particles in a reactor. Now, heavy water discovery was done by him. Okay, but he is also a person who discovered this art of thermometry and talking about ice volume effect in Earth's history. Okay, so now what he did is that he tried to design an experiment to relate the calcium carbonate which is getting synthesized in equilibrium conditions in presence of water. The interesting aspect which was not being seen at that point of time was that whether we will assume this water to be constant to talk about the composition of carbonate. So now there is a temperature relationship between temperature and the carbonate, but you must think in your mind that there is a composition of the seawater. It plays an important role driving the composition of the carbonate. So now that was a big puzzle, that how was the seawater varying. So he solved this puzzle assuming the seawater to be constant and trying to infer about the temperature based on the variability constantness of ratio in the sample. This is perhaps a compilation which I got latest, along with his work, which was largely done by this person called Sam Stein. He was a colleague of Urey. Okay, so he did work of calibration at that point of time in the 1950s. And subsequent to that, there are various calibration of calcium carbonate, and they land up in getting different equations where what you do is that you relate the temperature with the composition of the water and the carbonate and talk about the change in isotopic ratio in the carbonate as you precipitate at variable temperature. So now this becomes a specific tool when you try to do the thermometry. Okay. So now there are lists of other kind of experiments that people have done subsequent to this, where you relate What you relate is isotopic ratio of water, that of carbonate, and try to figure it out that what is the composition of that. Finally, what is the utility of this? You can use, once you get the temperature, you can talk about factors like how was the salinity varying through time, how was the ocean always saline, or it is largely non-saline. So now people have got a specific region and try to get reconstruction done for a specific region if this it can be applied to materials which are retrieved from specific regions around the world. So this is one such example that I mentioned about the Ghosh et al. He used this relationship because most of the samples which he has collected is from the ocean, and he got this relationship of which drives the composition of water at that location. So he used this relationship to infer about the temperature. He developed another relationship, but of course, as I mentioned, the variability between different relationships is very small, and if the relative change you are trying to address, you can always do that. But you need to probe the samples. People use different methods to say that my sample has not suffered for any kind of alteration. So what you are prone to, you are always prone to some kind of alteration subsequent to the deposition. So many things get altered. How do you alter? You alter it based on the water which is present in the carbon. So one such method for doing that is to first filtering out the samples, and that is done based on a luminescence property. So some of these elements which are transition elements which get incorporated have large quantity in your natural water. It alters the samples. So now we can see the presence of those kind of transition elements like iron and manganese. So you can call them as luminescence and non-luminescence, and try to see that those which are having luminescence property, they have relationship with isotopic ratio. So now there is some kind of filtering which is done to the data in order to restrict your interpretation and say that this is the primordial composition which is expected to be present if the sample would have not been altered. So this kind of filtering technique is used to get the best possible samples which doesn't undergo any kind of alteration. So this is one such reconstruction which has been done, talking about how the oxygen isotope variability took place, way from 245 millimeters to 65 millimeters. So what is shown in this figure is that if you talk about isotopic ratio, it varied with certain kind of kink which happened during the kind of Jurassic. But again, as you are seeing that the record may not be continuous at one location. It may be taken from different locations and you put it together to say that this is the average composition talking about the Earth. So now, if you think of spatial variability, there is less chance because many places you don't have this repository, this book which I am talking about. We are talking about some books where things have been recorded. So in many places they don't get recorded completely because you get partial record being preserved. So it is done in patches and then you stitch it. Okay? And stitch it to make possible that you can start talking about the variability of temperature which we have observed in geological past. Okay? Any question? We can interact. You have no question? You agree? What about a speaker some person? No question. If you don't ask question, I'll ask question. Okay? So how do you know that the water composition has not changed? The water composition has not changed, only the temperature has changed. Because that is a big problem when you apply the thermometer.
See, in my case, we are doing precipitation reconstruction. So when it comes to speedometer, the major component is...
So you assume the temperature has not changed?
Yeah, actually in my case, amount effect plays major role in temperature. In tropical climate, the temperature change is not that much as compared to in our temperate regions. So.
As much means there is a seasonal variability of temperature that you see in any place.
Yeah, but still it doesn't affect the delta ITO values as much as the precipitation does. So that the part plays a role.
Do you agree, convinced? Or you are not convinced, you wanted to check it? You are convinced. You will start with the assumption that there is no change in precipitation temperature.
So as far as the southern part of India is considered, the temperature won't play that much role. But when you are going to northern latitude, like northern parts like Himalaya, and you are doing the speedometer studies of that, there the temperature will of course play some role.
So how much is the temperature inside the cave?
So inside the cave, it's always in equilibrium with the temperature outside. So
Sure.
it's always in the equilibrium.
Not possible, no?
See, as far as I read, it's always opposite. In the
So now the thing which you should know is that inside the cave, you have a temperature which is different from the.
yeah, it's always opposite. Means,
Apparently, it will be different from what you have outside. And what about the moisture inside the caves?
moisture, we look out for caves which is always almost 95 to 100% humidity.
Yeah, but does it maintain throughout the year? Okay, so now when you think of equilibrium kind of precipitation, there are a lot of uncertainties in such kind of approach. Okay, you don't know how much is the uncertainty. So you are playing with something where there's maybe several factors which are playing important. Yes, you need to have 95% humidity level so that you can assume again that there will be equilibrium precipitation. Okay, if you assume the temperature remains constant, okay, you can assume that. So these are assumptions which goes into the model when you try to do the estimation. Model which is very simple, like a model which I am discussing is the linear model. Okay, but we make an assumption that there is no variability in temperature inside the cave, but largely it doesn't hold good. Okay, because anyway, if the outside temperature changes by a certain degree, the inside temperature will also change in certain magnitude. Now one has to apply such kind of correction, which is not possible if you use oxygen isotope thermometry. Okay, so there was always a need to develop another kind of thermometric approach to talk about exactly the temperature where you don't have dependency of the water. Okay, I'll quickly come to that, and there are few such thermometers. One such thermometer is calcium magnesium ratio in the sample. So now both this element they preferentially incorporate into the carbon. So now people have observed again there is a relationship between the concentration or ratio of these elements and the sea surface temperature. And they came up with another approach of doing thermometry when you talk about ocean sediment records. So people came up with this approach of doing thermometry using the ratio approach. So now will it work for terrestrial system? If you think of a speleothems, if you have magnesium calcium ratio, we need to talk about the temperature. So now that is requirement, that is need of the hours. Okay, so where you start probing this, but people have already started probing this. They have seen the relationship doesn't hold good in terrestrial records, it holds good in oceanic records. But the problem remains that this linear relationship get violated between basin to basin. Suppose if you talk about Indian Ocean, it is different compared to something which is in Red Sea, which is a different kind of ocean. So now this relationship doesn't hold good to take different basins. I will switch track. I will talk about something how to measure atmospheric CO2 concentration. But again, this is again one of the things which was discovered way back in 1990s. When people from University of Utah, what they did an interesting experiment where they analyzed carbonate sitting there formed in the root zone. So when you think of the root zone of a plant, what it does, photosynthesis, root, large, respiration, respire. They produce a lot of CO2. If you saturate the environment with a lot of CO2 and there is a presence of calcium in the site and water, you do precipitate calcium carbonate. So now what they have seen is that as you progressively go down into a spherical column, to a depth of 25 centimeters and below, you don't see large variability in the composition of soil CO2. It remains more or less constant. And they came up with interpretation is that this compositional variability is largely because of two factors. One, the diffusion which is taking place, the atmospheric CO2 from the top of the soil, and the second is something which is produced by the respiration of the plant. Okay. So now both of them they get saturated after 25 centimeter depth, so you don't change. So now if you can figure it out how much is the diffusion, okay, you can always try to see that you can measure the atmospheric CO2 concentration, measuring the isotopic ratio in the carbonate which is synthesized in the nature. So they designed this important relationship where this factor, as I said, talks about the soil character. So it varies between soil to soil, some of the soils they do require differentially, so they will have large diffusion with the atmosphere, and you can always characterize that soil with different SZ value, and just relate the atmospheric CO2 and soil CO2. And this factor, the other factor, comes from the diffusion, which is diffusion-driven mixing of atmospheric air and soil air, which takes place in the solid air interaction or interface. So now this becomes again another tool for doing reconstruction of CO2 concentration in the past. Okay, so people started talking about the CO2 concentration in the past using this as a how representative it is if you think of modern day CO2. Yes, it essentially gives you the concentration with some degree of uncertainty if you do such kind of measurement in the modern day soil. So based on that, and as I mentioned, stomata, based on acidic composition of soil, people have reconstructed back in time the CO2 concentration in the past. So now I'll go again switch track to tree rings, the person who may be interested in doing tree rings. So now what I mentioned in the previous discussion is that this ring gets deposited how? Annually. Okay. So when I say one of this ring, they get deposited in annual fashion. These are called annular ring. So what first thing you can do, you can measure the width of this ring. Now when you cut this tree, the last one will represent what? Which age? The last when you cut it. The time you are cutting, you can say that that is the last age. Okay? This is the last age at which the sample was cut. So as you progressively going back in time, you can talk about several years. You can see that here the width is very small. As you go to a certain condition, which is in the past, the width was much higher. The first thing which many of the people who work in the field of botany they do, they measure the width of this and try to see that how the width they change to time. So and try to see that that has to do with something with the local climate. And there in many cases people have seen that ring width has a relationship with the climate variability which is happening either in precipitation or industrialization at certain locations. There is a large relationship between both these factors.
The rings are created in the middle and they travel outwards.
No.
The outermost thing is bark, it's dead.
Yes. So what really happens is that you have air. The last ring is created here.
The last ring is the oldest.
No, it is Ulta. It is Ulta. Yes, it can't be. So we will meet again in the next tutorial where we will see that last ring represent the model. Okay, to start, the bark is somewhere which you are not seeing, it has been taken out. You cannot do anything with the bark. Okay, so in the last ring is something modern, and as you go down, this is the oldest. Okay? So it doesn't work in that engineering fashion, if you think. The plant behaves in a little bit different way. Okay? So now what really happens is that again, as I mentioned for oxygen, the carbon has again, how many isotopes? Carbon 12, 13. Carbon 13, 14, and carbon 14. So these two, they don't decay with time. This one decays. So this decays with nitrogen 14. And what is the half-life? This is the half-life. So we'll not bother this for a time being. We'll see that if we started bothering it at some point of time if I have something for the discussion. But how do we produce carbon 14? That you must know. Where do you produce carbon 14? Which location? Do you have carbon 14 in your system? And where did you get it from? Who gave it? The father, mother, none? Water? From where did you get your carbon 14? Huh? Acetic acid? Nitrogen disintegrated to carbon 14. So what happens in the atmosphere? You have a lot of neutrinos which are coming and neutrons which are coming. cosmic rays. It enters the atmosphere, it interacts with nitrogen to produce carbon-14. Okay, so this is getting produced anytime, but is the productivity varied? Depending upon the sun. If the sun is very strong, it is producing a lot of solar neutrinos. It comes and hits the nitrogen, it will produce more of carbon-14. The concentration of carbon-14 will depend upon solar activity. Sun has an important factor. So people have tried to do that. They try to relate that and try to figure it out that how the sun is behaving through time. Okay, because the sun is what I mentioned, the solar constant is not constant, it varies. Even in a seasonal scale, it varies from place to place. Though you assume it to be certain things which you use it for your numerical calculation, but it varies to a small extent. Okay, so now one can talk about solar activity using carbon-14. Sun, how it is behaving. So now what really happens, these other two isotopes, so we are talking about this two, carbon-12 and carbon-13, they discriminate. Discriminate means when you think of a plant, they like this when they produce organic matter. When there is a large photosynthesis, carbon-12 is preferred compared to carbon-13. The plant is lighter. Okay? So, and that results in some kind of fractionation. So, and this is what is described here because the photosynthesis happens mostly in the leaf of the plant. So now, if you have the composition which is there in the atmosphere which is designated by this, I have this in the leaf, that this is designated as a discrimination. And this discrimination factor is again driven by the ratio which is Ci/Ca. What is the concentration of CO2 inside and what is there in the atmosphere. So if you can I get this discrimination, you can talk about the variability of CO2 concentration in the atmosphere. So people have used this to talk about the CO2 concentration variabilities in the past. Okay, so now I'm going to skip this because along with carbon, one can also use oxygen discrimination to talk about how the water use efficiency in the plant. So now this has also been, people have done an experiment where they have analyzed the oxygen discrimination and relate it with equilibrium and something called process like kinetic fractionation within the plant. So now when you talk about equilibrium process, do you know what is the difference between equilibrium and kinetic process? What is equilibrium? Are we in equilibrium right now? No, I don't think so. I don't think so. All of you may be in equilibrium with each other, but with me, no. So there is a kinetic effect. So that is the difference, that when there is a large difference in terms of two environment, in terms of phases which are talking to each other. If such situation comes, and such situation can come when, in this case, if I go very fast, okay, I start doing a lot of kinetic effect in the system. Or I go very slow, you might feel sleepy. Then you will not be in equilibrium. So right now you are attentive, but I don't think that we are in equilibrium. Maybe all of you are in equilibrium. I don't know. Maybe she is not. She knows a little better compared to others. So now, thing is that once you have kinetic effect, mostly when you have large kinetic effect, you start producing more or you start running more. Metabolic activities start enhancing. In such situation, you have kinetic effect. And that leads to another fractionation or discrimination, which you need to take into account when you talk about oxygen isotope variability, but you don't need to take into account when you talk about carbon isotope variability. When there is such discrimination, that means evaporation taking place, large evaporation taking place, you have large kinetic effect. Okay, suddenly you start having a wind coming into the picture. So, which will take out whatever the moisture relative humidity in this environment, reduce it drastically. You will have kinetic effect. You will have large transpiration happening from the plants. So that leads to kinetic effect. So these are examples where you have variability of kinetic effect. So what you can finally get is this parameter, which is effective enrichment of leaf water. And if you know that, perhaps you can talk about how the water composition in the environment is varying through time. If you assume that kinetic effect is negligible, okay, for her case, if you are precipitating calcium carbonate in the cave, which I am not going to discuss, If there is a large fast precipitation, it may not be in equilibrium. If the precipitation is very slow, it will be in equilibrium range. If there is a large degassing happening, ventilation happening, it will not be in equilibrium. Okay? So this effect will be more or less similar. It will mimic. So you can generate one such relationship for your case. And again, you start talking about evaporation, which is atmosphere and leaf water vapor, how much is they are talking to each other by doing the ratio. So, because the stomata will regulate. So what happens that the stomatal opening, they will regulate if you have more either CO2 or water vapor in the environment. If you have more water vapor, what does the stomata do? They close the valve. I don't know. If you have more CO2, I close the valve. If you have less CO2, then open it up. That's how stomatal regulations happen. And that is essentially triggered again by the hydrological condition, because you have to finally give osmotic pressure to open it or close it. Okay, so now that regulation is very critical when you think of interaction with the atmosphere. And this is again a demonstration of that transpiration where you open it up and the stomatal cavity becomes bigger or smaller, and you have large flow of materials from either internally or outside depending upon the environmental condition. So what has been seen is that there is again a relationship between isotopic effect and the temperature, and one can essentially talk about how temperature reconstruction to measure the oxygen isotope ratio in plant derived material. This is another new approach which is called TEX. That means alpinum-based approach. Organic chemists usually talk about this TEX86, that is the molecule where you have a carbon atom, where you number molecules of 86 numbers. People have seen that that can give a good estimate about the temperature. So the excess of it, more in concentration of this, will lead to change the compositions of the plant material or the material which is getting derived from any organic elements. So there are many papers talking about it. Again, what has been done is that the TEX86 has been correlated with many phytoplanktons which have been having organic matter, and again they are derived a linear relationship. So if you have now the TEX86 being measured in your sediments, you can talk about what's the temperature in the past. So this is again another approach. So now what really happens in terms of doing paleoclimate reconstruction, people are not believing one approach, but they do multi-proxy approach to talk about the same temperature. And they get convinced that are you getting particular temperature which is consistent with each other. So that leads to the prospect of another proxy or reconstruction method or thermometer. So these are different thermometers which has been discovered with a specific need. Now in this thermometer, you have to use organic matter. So instead of using inorganic, which earlier I have discussed, here people use organic matter and try to correlate it with their composition variability, the ratio of 86 in the sample, with temperature, and derive the temperature information with a linear relationship, assuming that it is linear, of course. This is again the SST reconstruction of early Cretaceous based on TEX86, and which is another proxy for getting temperature of the past, and it is largely similar to what has been observed using other proxies. So one of the modern development of thermometry in terms of oxygen isotope came in rather recent time, in the year 2006, when it was discovered that when you have molecules which are having few of these species instead of one barrier. So now when you talk about isotopic exchange reaction, what you talk is this molecule's CO2. Now the CO2, carbon, you know that carbon 12, you have 16 and 16, it makes 44. So now you might have possibility of getting carbon 13. As I mentioned that carbon 13 also exists. So if you have carbon 13, 16, 16, it makes mass 45. You take into account this minor composition from this, doing a mathematical treatment, then you can measure the carbon 13 in your sample. The similar way, if you have 46, it talks about O18 in your sample. So people measure O18 ratio, measuring the CO2 composition using an instrument which is called mass spectrometer. This is the instrument which is mass spectrometer. What are the essential components of mass spectrometer? Have you read about mass spectrometer any time? Class 12? No. Have you seen mass spectrometer? So this is the mass spectrometer. It's elephant. Okay. So now it has, here it is source where you produce ions. Okay, you ionize your gas in this chamber. And then what you do, you give accelerating voltage to the ions and allow it to subject it to a magnetic field. This is a magnetic field. And you collect it on the other side of the collectors. There are Faraday curves which collects this. This has been in mass spectrometer. Mass spectrometers allows collection of all the ions which are of different masses, and you can measure them with such sufficient accuracy. Okay, so what you measure is the ratio between minor with major, and which tells you about the compositions of materials like O18 in your sample, oxide isotope composition in the sample. So for the carbonate, that is how the measurement is done. So now this thermometry, they talks about 16, 18, 30. Okay, 47 meaning the CO2 molecule. And this thermometry was discovered with the intention that it will give another handle to the already existing thermometry, which is oxygen isotope thermometry. But we found out that it gives much better information. Okay. So now what you do is that when you try to take a gas and subject it to a very high temperature, the gas becomes much more random. So imagine you have all these molecules which are heavy and light in your box. And if you take this and all these molecules to a high temperature, what will happen? You will start shaking vigorously. So you get something which is stochastic, largely random. So we call this as our standard. We define this randomness as we take the gas to higher temperature and measure the composition which is present there. That means what you analyze and compare it with something random and assign a 47 axis to the sample. This is a definition which was used for defining this thermometry. What lead to is that we got a relationship where 47 is governed by temperature. So now you have largely a relationship which is given by a temperature equation. So later on, what really happened is that people were not convinced with this thermometric approach or the linear equation. What they did is that they analyzed various materials from different sources with known temperature history and validated this thermometer. So now this is another thermometric approach where you get the temperature of carbonate formation. Okay. Once you get the temperature of carbonate formation, it has nothing to do with water, because I have removed the water component which was responsible, assuming that I am taking my standard which is stochastic, which is random. So my approach doesn't allow the water composition to come into feature. So this gives you independent estimates of the temperature, and if you have now the oxygen isotope composition of this, you can talk about the salinity of the environment. So this is again another thing which has been done. So now I gave a summary of all the informations which is required for doing the thermometry, which is relevant when you talk about what? Temperature reconstruction in the past. So now one can take different materials, use the data bank and try to retrieve the temperature. So you will do a couple of tutorials to handle that how you derive the temperature informations or the water composition, okay, in your afternoon session. Okay, so I will try to quickly go now and talk about biogeochemical cycles and see that how far I can progress. So when you think about biogeochemical cycles, we talk about all these different components, water, nitrogen, carbon dioxide, phosphorus, sulfur. As I mentioned that when you try to create a biota, phosphorus is very important. That is what you are born in your constitution. So now, many of these elements or compounds, they cycle. Cycle means they move around, okay, in different compartments of the earth. What are different compartments? We talk about atmosphere, we talk about hydrosphere, it comes to lithosphere, sometimes it goes to cryosphere. Okay, so they cycle. Now if you think of life, life requires a set of less elements which are set in rain, but you do need to have set of other elements which are not either red or orange in a small quantity, or else you cannot survive. Okay? So now, if you think of yourself, you are mostly composed of carbon, nitrogen, oxygen, phosphorus, sulfur, and some amount of chloride in your body. Do you have potassium and sodium? Why do you need it? To regulate osmosis, important factor, okay, which regulates flow of fluid in your body tissues and cells. Okay? So this set of elements, they usually, most of the cases, they usually cycle. They goes in some kind of path. They comes back. They cycle in that sense that you will start eroding it. It goes to another phases or another structures, which can be water in some cases, and in some cases to the ocean. It gets deposited in the ocean floor, and then it comes back. So we'll talk in little details. We should switch off this light, or it's not visible. Anyway, this is a carbon cycle. Okay. So the idea which has been shown here is it visible? No. So this is what you have the CO2 in the atmosphere. So now, what is the major source of CO2 in the atmosphere? Ultraviolet ray. Or what? Be louder. Phosphorus. What? Louder. No. Volcano. I told na. Natural source of CO2 is volcano. So you have CO2 in the atmosphere. How does the CO2 is taken with the plant?
Photosynthesis.
And see, the CO2 which you have in the atmosphere, it is majority of it is coming from volcanoes. Or else from where? Respiration. Anything else?
Yes, weathering.
The difference is volcanoes. Respiration.
Weathering.
Fossil fuel. So what you was telling? Ocean. So ocean usually respire. Does it respire? Phytoplankton. And why do you respire? Why do you do respiration? All of us do respiration. We burn fossil fuels. Why do you do this? When you do oxidation, that is the only mode of generating energy. For any kind of energy generation, you need energy. When the plant does it, if you need that energy, you need to burn carbon from some source. Okay, so now we need energy, that's why all these fans, tubes, they are on. So because we need to see and talk. So we are generating energy and we are producing CO2. You cannot stop it. It's a requirement. But we can minimize it. Okay, so now CO2 gets produced and then it is taken by plant. If there is some other mechanism by which the CO2 can be taken, the CO2 has been taken by the plant. Okay? Is there some other mechanism by which you can take the CO2? I mentioned this in the last. Huh? Ocean. What you should do to the ocean so that CO2 start coming? Huh? What you should do to the ocean so that it start dissolving and going inside? Can it do? Ocean can take the CO2 in? No. Yes.
Yes.
If you assume soda bottle to be ocean, I can cool the soda bottle and the CO2 will be inside. Okay? As soon as I heat it up, this is from the simple law of physical chemistry called Henry's law. So now if you heat it up, you'll build up a pressure. If you shake it a little bit, you can use it for some other purpose. Okay? So now the soda bottle is a perfect example where sinking happens. If you cool the ocean, CO2 is taken by the ocean. Okay? And the CO2 goes where? Becomes dissolved in the ocean. Okay? So whatever the CO2 which we are dumping into the atmosphere right now, it is going to the ocean. What it should do to the ocean? Ocean is acidic.
Acidic. It increases the acidity.
Ocean is acidic or it is alkaline? So most of the time ocean is acidic or what? Alkaline. So ocean is alkaline. So it should tend toward acidic condition if you dump too much amount of CO2, because it produces acid which is called carbonic acid. Okay. So if you dump too much amount of CO2 into the ocean, it will make the ocean acidic. And the first thing which will get affected will be corals.
Corals and crustaceans.
They will get affected because they will not be able to tolerate it. Their shell will get affected. Okay. Is this happening?
Yes.
We will quickly go through some of the evidences. Okay. We will skip this. Okay. Have you seen this? You have seen this. What is this? This is Killing's what? Killing guard. What does that mean? Killing has not done. Killing has gone, now Killing's son is there. Okay. Killing has gone. So Killing, his name was C.G. Killing. Okay. He thought that he will start first measurement of atmospheric CO2 from middle of the ocean. He thought that he would measure atmospheric CO2 from the middle of the ocean from the island called Munalwa. Munalwa is in Hawaii. Okay, so now this observation comes from the island which is Munalwa, which sits middle of the Pacific. And what he started recording right from around 1956 onwards is some kind of seasonal variability which you are seeing of CO2 concentration. You can definitely see a pattern which looks like this. This has been exploded. One of this has been expanded to show it to you that it is seasonal pattern. Okay. During the time of winter, where is Hawaii? Most of you know where is Hawaii? Northern hemisphere or southern hemisphere? Southern hemisphere. Very good. It is in the northern hemisphere. Okay. So it is in the northern hemisphere. So when the northern hemisphere experiences winter, that is during the time of January onwards, you start building up the CO2 concentration in the atmosphere. So you start dumping a lot of CO2 in the atmosphere. And during the time of summer, you start dropping it. Largely it is driven by respiration and photosynthesis. Largely. Okay. But in a seasonal state. But when you try to see that through time, what is really happening is that you are building up the CO2 concentration through time. And this place now becomes some kind of representative of global CO2 concentration. If you wanted to type this term called Munalwa CO2 concentration, you can see yesterday's measurement, what they are measuring. So recently there was a news that it has exceeded 400 ppm, the CO2 concentration. Okay? So
why CO2 is having a peak somewhere and then
this and this. Huh?
Yeah, seasonal cycle.
I explained it, na? During the time of winter, what happened? You go on. Lot of fossil fuel to you.
Like a mid-ocean.
Now CO2 is a gas which is very well mixed. Okay, it takes not say it takes about say 50 years to be there in the ocean atmosphere before it gets stuck in the atmosphere or ocean. So now CO2 is a very well mixed gas. So it's a fast moving gas, it diffuses very fast. Okay, so that it is homogeneous to some extent. Okay, if you talk about Bangalore concentration and the concentration there in the Divecha and Glacial, there will be difference of the order of about 50 ppm, not much. Okay, so now since this location, which is the middle of the ocean, Munalwa, it is taken as representative stations analoging the world CO2 concentration, and where you have long-term record of CO2 variability. Okay. So now your question was that why CO2 concentration builds up during winter in the northern hemisphere? Is this your question? Because in the time of northern hemisphere winter, what do? You start burning more fossil fuel. The second thing you do, you dampen the productivity. Photosynthesis reduces. Why? Because many of these trees which are deciduous, they shade their leaves. You will see that they are no longer there in here. If you go to little higher altitude, okay, leaving the equatorial belt, you will see this is a feature which is mostly the plant. They shade all their leaves. If you go from A to D, for example, in the time of winter, they shade their leaves. They don't do much of photosynthesis. So, what really happens is more respiration. So, buildup of CO2 concentration is because of both drop in the productivity, more fossil fuel burning. Okay, drop in productivity will not allow the things to come down. Second, and it will allow buildup of CO2 concentration. And during the time of summer, what happens is you have rainfall. You have IISc, for example, getting formed. It brings a lot of distilled water to the continent, which is having a large, when it interacts with the rocks, it derives productive effects. And it makes ocean more productive, land also more productive. It sucks out the CO2. So it has not dropped in the CO2 concentration. Does it make sense? No. So you want it to be pulled up. Like you wanted the dendrochronology things to be pulled up. Will the ulta satisfy you? No. Tell me, during winter you are more productive. You? You are always productive.
Because every winter we have a very black color. So
In winter you have large black color. Why?
yes, we want to receive and learn also.
I have half an hour. 1 o'clock is your lunch. Yes. I will hold you for another half an hour. You have to tolerate me with few more details. So you are convinced? Okay, fine. So we will proceed. Anyone not convinced? Yes.
This helps so that the CO2 concentration vary with the year. It was per day CO2 concentration vary in a particular
Day. Yes, it does. If you measure it continuously, you see that it is dropping down. Okay. Yes, it does. Because of the night time, what happens? Tell me again. In night time, what happens? You have photosynthesis? No photosynthesis. You have? No. Yes. Photosynthesis requires what? Sunlight. Sunlight. Unless you have it, you can't do photosynthesis. So night time, no photosynthesis. Okay? So you will have all this only the respiration. It builds up. So night time you see high concentration of CO2. Okay? And what happens in the daytime? It drops down. So you will see another cycle like this, but it will not be as intense as this. This is very well seen in terms of ppm level. Okay? So there will be also cycle, but it may not be visible in that extent. But yes, you will be able to see some cycles, which is called dynamic cycle.
in a particular day, how much variation
In a particular time.
in a particular day,
How much? So that also varies from place to place. For example, if you are in a city, it varies drastically. Night time you don't drive. Okay? You don't respire. You don't energy. Nobody pays you in the night time. You sleep. Correct? In the daytime, all of us go for work. I drive my car, come and give a lecture. I burn CO2. Correct? Sure, but no. And if you go to the urban areas, the system, their amplitude will drop down. So in the rural area, the amplitude will drop down. In urban area, we have high amplitude of variables. If you go to the rural area, you will start dropping. Okay. We do such kind of experiment. Okay. We do such kind of experiment, try to figure it out. Night time, daytime variability. There are other interesting phenomena which happens, which relate to something called nocturnal inversion layer. Do you know what is nocturnal inversion layer? So which allows building up of CO2 concentration rather very high in early morning time. So it traps all the gases to the surface, close to the surface. As day comes, you start having large missing. So inversion layer vanishes. That inversion which you see in the night time vanishes. So you see well placed layer in the daytime. Interesting question. Are you satisfied with the answer? Satisfied? So what do you work on?
If you want how much variation, maximum variation, how much maximum variation possible in urban
That again I am telling urban area.
area?
Yeah, it can go to 10 20 ppm some cases. 10 to 20 ppm. So we did a funny experiment, you know. And one of my students who is sitting here, she can show you, tell us the result of that experiment that there was a time when the solar eclipse happened. The solar eclipse happened at the time of day, around 12 o'clock. You cut off the sun. So suddenly you start bouncing back to CO2 concentration. Productivity reduces. Okay? And you can quantify how much a city like Bangalore, if you do several places the same measurement, it's producing CO2, which is not getting well mixed. Because you have, and there is no photosynthesis happening at that point. And those kind of rare opportunities comes once in a while. We did demonstrate that yes, if you cut out the productivity, this becomes source. So if you cover this place with what? Concretes, you start generating more CO2. Correct? That's why people are saying that you should have some productivity, have some plants. Okay? City like New York, for example, it's all with concrete issues. There you will not see much variability. It is always very high concentration. Nighttime, daytime, variability is only because of inversion, nothing else. Productivity is not a factor. Important factor. So when you try to derive this information about different CO2 concentration in different phases, like for example, emission driven, something with the atmospheric and productivity, people use isotope as a tool because they have different compositions being recorded in all these materials which are dumping CO2. I will just show you that if you have a respiration taking place from a plant, the composition which comes out is around minus 26 Kelvin. If you have coal getting combusted or fossil fuel, like you have a power plant, it gives a composition of minus 28. When you compare this to the atmosphere, it is minus 8. So there is a large difference between this two. So now you can imagine this is something a water, and that you are mixing this two material, which is blue in color. So what really happens is that air undergoes some kind of mixing at different point of time, and you can identify it provided in nature its isotopic ratios in those phases or time period. Either it is diurnal or seasonal. Okay, so people use this to quantify with time that how much all this atmospheric increase, how much is emission increase, and how much is the sinking happening. Okay. Now, if you think of the CO2 concentration back in time, you can go back in time. This is this has the less. So now this is the place where you have what you call modern day crystallization, and you come to a time when it is 1800th century, where you have ice cores which are recording the CO2 concentration. So ice core traps a lot of air when it gets formed or ice get formed. One can analyze them and try to find out that how much is the CO2 concentration. So the pre-industrial value, people take it around 280 ppm. And from there, we are slowly increasing it. So now, ice core serve as one of the purpose for doing this. So now, what people have seen is that together with the CO2 concentration, if you measure this isotopic composition of that, there is an inverse relationship of both of them. So now CO2 concentration is going high, the isotope is going lighter and lighter. So there is inverse relationship, and what if you do some kind of model of plotting them, that CO2 concentration in the inverse algorithm, that is the 13C, you derive a linear pattern where you can talk about the end-member composition. So this is the source value, which is 24.89. So I mentioned that fossil fuel, and when you talk about the plant, they have respired component which is around minus 25 and 28. So this comes roughly in between, suggesting that respiration and photosynthesis are the end members. So you can figure it out that how much is the respiration and how much is the natural air getting mixed in one particular environment. Again, in this relationship between carbon isotopes and the CO2 concentration, there are situations when people have seen poor anti-correlation. That is, somewhere the anti-correlation is very strong, somewhere it is poorly anti-correlated. Those situations are exceptional where Earth experiences either ENSO kind of situation, okay, where there is a large respiration which is happening, and when you measure into compositions in Mauna Loa, you will start, the manifestation of that is seen in the atmosphere. Okay, so now if you try to infer about the CO2 concentration in the past, one can use tree rings, because again, as I mentioned, the tree rings do have some relationship to atmospheric CO2. People use tree rings to talk about the CO2 variability in the past, analyzing this carbon isotopic ratio. This is one such example where people have done reconstruction going back in time, showing that modern time, the composition is this. So in the time, more composition is getting more depleted. This is a modern tree ring. When you try to see the tree ring which is older, it captures the composition is rather very enriched. And one can, this data set has been inferred based on this ratio and using the relationship which was proposed by Farquhar. So talk about the composition of CO2 in the past. So we'll do one such exercise as a tutorial to figure it out, that whether you can really talk about the CO2 concentration if you analyze the tree rings as a proxy. We'll quickly go and see that how the ocean behaves. So now this is again Mauna Loa observation, which I showed. And this is again the observation which has been close to the stations from where ocean has also been monitored. So what has been seen is that ocean respond in the same way as the atmosphere. Ocean composition was also changing. And this gets reflected when you see the pH. It is getting with time more acidic. So this is a famous experiment which was called Aloha experiment, where it has been demonstrated that the CO2 concentration which is going high in the atmosphere, eventually it goes into the ocean, and the ocean acts as a buffer system where you start changing the pH towards more acidic. And people start now suspecting that if you start doing this in a long period of time, you will destroy all the corals which are there in all ocean islands like Hawaii and other places. So how the ocean does this in terms of equilibrium? So the ocean, the CO2 which is there in the air, it interacts with the ocean. First it gets dissolved, and then there's a process called hydrolysis, and then you have hydrolysis. Finally, what really happens is that if it gets saturated, form calcium carbonate. The overall reaction is this. So now, if you can see that if you make the ocean acidic, the calcium carbonate, which is the kind of shell in which the organism stays, they will not be able to secrete it because you will not have enough amount of carbonate ions which will get precipitated as bicarbonate. And the solution will be deprived of any kind of carbonate. So now, the secreting organisms will not able to precipitate their shell, so eventually there will be a process of extinction. The corals may wipe out from this planet. So this is one such example where it has been shown that around 280 ppm, which is pre-industrial value, if you have 280 ppm in the atmosphere, the 8 ppm goes in terms of carbonic acid. Bicarbonate will be around 1600 ppm, and you have carbonate ions will be 268. So now, if you double it, amplify it, if you make the atmospheric CO2 concentration 560, you essentially start. What is happening is that you have this, but you are dropping down this carbonate ion. So essentially, what I am trying to explain is that the shell, or all the shelly organisms, they will be eventually not able to precipitate because there is not much of carbonate in the environment. Any question? Is this convinced? No. Do you think it is happening? It happened in the past. But in the time of Paleocene, Miocene, when I told that there was a high CO2 concentration, so most of the organisms, they don't used to prefer on the surface of the ocean. They used to be mostly benthic. They used to leave bottom of the water. Okay? Okay, because they cannot secrete calcium carbonate staying on the surface. So planting species will be rather very small in abundances compared to something which is there as a bottom dwellers. Okay, so now that people have documented. There are large documentation of abundances of species through time in terms of plantic and benthic. Plantic are those which floats. Benthic are those which stays in the bottom of the water, ocean floor. So people have seen the ratio of this has changed through time. Time's up. You are giving alarm. Okay. I don't have much now. Maybe I'll talk briefly about nitrogen cycle. So when you talk about the nitrogen cycle, you know that atmospheric nitrogen, what is the kind of concentration in the nitrogen in the atmosphere? 70%. 78%. I see. So now, when you think of nitrogen in the atmosphere, where it is produced from? What is the major source of nitrogen? Soil. What? Plants. So nitrogen can be treated as a normal gas. Is it inert? Is it inert? No. Reactive. How can you react nitrogen from nitrite? Is it easy? Difficult? You need a lot of energy. And who gives this energy? Where do you get nitrate formation in the atmosphere? Bacteria. You do get a lot of nitrate formation there in the atmosphere because of somebody told something which is right. Lightning. When you have large discharge happening, you produce a lot of nitrate in the atmosphere. So once you produce that nitrate, what happens to that nitrate? It gets dissolved in the water. It can come down as nitrate. In addition, there are bacteria. For example, all the legumes, they have bacteria in their root zone. They fix nitrogen selectively. Okay? So they fix nitrogen selectively in the plant. So this process is called assimilation of nitrogen. So as soon as this assimilation happens, which is in the form of a nitrate, there are other processes which destroy it. Okay, there are denitrifying bacteria. We denitrify this and put this back into the atmosphere. Okay, so nitrogen fixation happens mostly in the root zone, or it could be in the atmosphere, and you get dumped this as a form of nitrate. In many cases, what happens that you have participation of bacteria, which are soil bacteria, where instead of converting to nitrate, it converts them into ammonia or ammonium. Okay, so instead of oxygen, here you prefer hydrogen. Okay, and that gets assimilated in the plant, and finally you might denitrify it and put it back into the atmosphere by the process of denitrification. So now this cycle is in operation. Okay, so now most of the time what you do is that you allow the plant productivity to rise, adding what? Adding nitrogen fertilizer. One of them is urea. You add them. So urea do get produced from taking the nitrogen from the atmosphere. So but it enhances the productivity. So once you enhance the productivity, what really happens? If you enhance the productivity, you will have more bacterial activity, so you start denitrifying. So because the soil has a capacity for denitrification, so if you exceed that capacity, you will destroy the soil and you may not cultivate. So usually the farmers, they are very clever. What they do is that they allow fertilizer to be used, and the next season they don't allow fertilizer, they use organic fertilizer. Okay, to make a balance so that they have good productivity in their field. Okay, so nitrogen also has isotopes. What are the isotopes of nitrogen? N15 and N14. N14 is major. Their ratio, they do get changes if you change any of this path. if there is a large nitrification happening or denitrification happening.
So time scale of nitrogen cycle.
Time scale of nitrogen cycle in what extent? I mean, what time scale?
How the cycle.
So nitrate, this can be seasonal. This is very fast compared to CO2.
So it replaces.
Yeah, so now there is no dumping yard for nitrate or ammonium. Like you have carbonate which is getting formed, it gets dumped where? Into the ocean. So if you think of nitrate, sometime it gets deposited if you go top of the mountain. Okay? Because, why? Because the top of the mountain, you have dry environment. If you have a rainfall there, it has large amount of nitrate which has been taken due to lightning. It dumps it there. Okay, it gets produced there in the lightning and get dumped. So, many of the places where you get nitrate, they are formed because of this process, where you have large lightning, production of nitrate and dumping it with the rainwater to the environment. Okay. So one of the famous example is Chilean nitrate. So nitrate is used where? In gunpowder, ammunition. Okay, so the Chilean nitrate becomes very famous because they started, usually the nitrate gets produced by Haber's process, that you know. Okay, but that is the mechanism. But if you have a natural nitrate which you can explore, you add it up. So during the time of World War, Chile became very rich because they supplied nitrate to the other part of the world as a gunpowder. Okay, so the mechanism of nitrogen fixation, is it clear? No? What is the way you will fix nitrogen?
Bacteria or
Up to you. Did you understand fixing nitrogen? I am asking you. Yeah. Tell me. No. You didn't understand. So I am fixing it as a nitrate. How I am fixing it? Bacteria is one. I told another process. Lightning. When you have lightning, atmosphere has nitrogen and oxygen. It produces nitrate. Okay? And then it comes with the water. Earth surface.
Lightning comes with the answer.
Right? But the lightning happens there in the atmosphere. It gets produced as nitrate. So why should it come at the Earth surface? It will come eventually to the Earth surface if there is a rain. Okay? Or else it will come as a deposit of aerosol. Okay? These are the two mechanisms. If the dust particles get formed, which is big enough, it will deposit as aerosol. Or it will come through water. Majority of the time it comes through water. Okay?
so what happens to the soil productivity? You're saying that decreases over time if you are using too much urea. The concentration of nitrate will increase as we are using more and more.
So nitrate is very essential nutrient for the plant. You need nitrate to a certain limit. If you don't have it, the plant will not grow. So if you have more denitrification happening, okay, if you have large bacteria which are getting colonized in a system, okay, which is denitrifying, so what will happen? All the nitrate will get converted into nitrogen. So you will soil will have no nitrate.
So more urea you are using, more nitrate you are putting, then you are increasing more denitrifying bacteria and that.
Correct. So you allow more denitrification to happen. So you destroy your field for productivity for a certain period of time. Okay, this is the repetition. So now this is some kind of compilation. Somebody was asking that, you were asking that what is the kind of different budget of nitrogen. So this is a compilation of different budget of nitrogen which is coming from different places. So now if you think of primary rocks, it has some amount of nitrate, but majority of the nitrate recycling happens because of atmosphere, okay? And one of the important parameters which dictates nitrogen is carbon in the system. So there is some kind of relationship between carbon and nitrogen in the system which is called CYN ratio, which people use it to designate materials which are productive and materials which is non-productive. If the material is very highly productive, CYN ratio will be less or high? Less. Okay, nitrogen will be more in the environment. if the material environment becomes non-productive, the C/N ratio will be increased. Okay. So the nitrification, denitrification one can study based on C/N ratio itself. So now nitrogen, as I mentioned, has isotopes, and if you go in a food web from algae to carnivores, you can see that there's a large change in terms of enrichment or heavier.